So the term flux consists two factors. First of all, a vector quantity, and second, area. As we have learned in line integration, line integral is defined for a vector quantity and a displacement vector, and line integration is sum of dot product of this vector quantity and displacement vector along a curve. That is the line integration. Similarly, flux is defined for a vector quantity and a given area. So we know the vector quantities are displacement, velocity, forces, electric field, magnetic field, and gravitational field, and there are many vector quantities. So vector quantity, a physical vector quantity such as force, that force. So a particle may experience a force of 5 Newton. Let us say, for example, the particle experiencing force for 5 Newton. Here a force is being exerted at this point. Or this is point A. So this force is concentrated only at this point A on this object. So this force region is only limited up to point A. That is also defined for the vector quantity. Similarly, when we talk about term flux, we talk about a distributed vector quantity. Here you can see 5 Newton force is applied at point A on this block. So this 5 Newton force is limited to point A only. Here, or at other point of this block, no force is being experienced. But when we talk about term flux, we talk of field. This field can be any physical vector quantity such as velocity, force, any other vector. And this field should be distributed in space. Field is nothing but a distributed vector quantity in space. Any distributed vector quantity in space can be assumed a field. It can be a velocity vector field for a flow of fluid. A fluid is flowing through this section. It will have different velocity throughout this cross section. So we can say velocity vector is defined in this space, that is field. Similarly, we can call gravitational field, electric field, magnetic field, any vector quantity which is a distributed vector quantity in space. At different points in space, its value and direction is defined. So for example, we will take very simple example here. Generally, a vector field is defined as a function, vector function, in terms of I, J, K. Let I, J, K are unit vector in x, y, z direction, positive x, y, z direction. So at a point x, y, z, vector field at point x, y, z can be defined as function of x, y, z I plus another function let h, x, y, z j plus another function let k of x, y, z. So you will write it L, and here unit vector k. So a general vector field at point x, y, z, that is, simple meaning is this: at point x, y, z, the magnitude of this field and direction of field is given by this vector I, J, K, these are unit vectors in x, y, z directions, and these are functions of x, y, z, f x, y, z, h x, y, z, l x, y. These are function of x, y, z. Put the values of any point in these functions, you will get a vector field for a particular value. Let x, y, z is equal to x0, y0, z0. For a particular field, you will find vector field in terms of ai plus bj plus c. These are just functions of x, y, z. H, x, y, z. H is a function of x, y, z. L is a function of x, y, z. F is a function of x, y, z. So when you will put a particular point x0, y0, z0, that is 2, 5, 7 or 8, 9, 10, whatever it is, a specific point, put the values of x, y, z in these functions, you will get a vector in terms of a, I, b, j, c. And this vector is nothing but a field, magnitude and direction of that field at point x0, y0, z0. That is the meaning of vector field. So we will just have an example to describe how the vector fields are defined in space. So we know that this is a coordinate axis, this is x, this is y, this is z, and unit vectors are k, I, j in x, y, z directions. So let a mass is kept at origin of magnitude m. A mass of magnitude m is kept at origin at a distance r from its center. This is a displacement vector and this point is P. At point P, we know gravitational field GP. GP, that is gravitational field, is given by Gm by r square. Simple formula we all know. So how we will represent this field in vector function form, in the form of vector function. So this is the magnitude of field, and the direction of this field is radially downward. Direction of this field is radially downward towards the center of this mass. So we can write it. Now we have to find a gravitational field in terms of vector function. So the magnitude is known. Now let this point is x, y, z. So the position vector OP can be written as xi plus yj plus z. Position vector OP, or you can say vector r, can be written like this. So vector, similarly, unit vector r divided by mod of r can be written as OP by mod of OP as mod of this vector divided by its magnitude. So we know for a point P having coordinate x, y, z, its position vector is given by this, and the magnitude of this vector is under root x square plus y square plus z square, that is distance from O to P. So unit vector in this direction will be this vector divided by its magnitude, that is xi plus yj plus zk divided by under root x square plus y square plus z square. So this is unit vector. Let us call it r. This is unit vector in radial direction. Now we want to represent vector field in the form of vector function. So in this form we can write it G. So we can write vector G at point P is equal to, we are finding the field, gravitational field at point x comma y comma z in terms of a vector function. Gp is Gm divided by r square, r is the distance, into vector r. This is unit vector, this vector, unit vector, unit radial vector towards point O. Sorry, this unit vector is from O to P, but we want to find vector from P to O, because this G, direction of G is towards this center of mass. So negative vector, that is, we will write it minus r. Vector r is vector OP, O to P, but we want to find a vector PO, that is P to O. Unit vector in PO direction will be minus unit vector r. Minus r. R is the unit vector in OP direction. With we want unit vector in PO direction. So that will be minus r. We have put minus r here. So this is the vector field, gravitational field at point P. We want to find in terms of x, y, z. Then you can write it Gm divided by, r is the distance. Distance is under root x square plus y square plus z square, and r square will be, it will remove under root x square plus, so r square is x square plus y square plus z square, and minus r. Minus r. R is this vector, unit vector in OP direction, but we want unit vector in PO direction, because direction of G is from P to O. So we have found vector G is, this is the magnitude of vector, and this is the unit vector from P to O, which is the direction of field vector G. So minus r. We know r, this is the r vector. So minus r will be, put minus sign here, and this is the r vector. Xi plus yj plus zk divided by under root x square y square. So we can write gravitational field in the form of function, vector function. In the form of vector function, this field, gravitational field, can be written as minus Gm xi plus yj plus zk divided by x square y square plus z square power 3 by 2. This will be expressed at power 3 by 2. So this is the vector field at point x comma y comma z. Gravitational field at point x comma y comma z is given by this vector function. Gravitational field due to this mass located at origin of this Cartesian coordinate axis at point x comma y comma z is given by this vector function. This is the standard form of vector function due to gravity. First of all, to define flux, we must have a vector quantity which should be distributed in space. A distributed vector quantity in space. That is the first requirement of flux. These are the components of flux, you can say. A distributed vector quantity, and second, a area. Area means a region through which a particular vector quantity, physical vector quantity is passing through, is existing and passing through. Because vector quantity has directions. Due to its nature, they have direction. They can pass through this area in vector form. They can have this direction along this area. In that case, we will say that vector quantity is not passing through this area. Similarly, flow is passing through this area. That we can say that flow is passing through. That vector quantity velocity is passing through this area. And if flow is in this direction, in that case we will say flow is not passing through this area, because vector quantity has direction. That's why we can say vector quantity is passing through a particular area, or it may not pass through that area. It may be parallel to the area. So, if we define the flux, flux is defined as extent of a physical vector quantity. The definition, this simple definition of flux is the extent, it defines the extent of physical vector quantity through a area. Extent of physical vector quantity through a given area. That extent is called flux of that vector quantity through this area. So to explain this flux, we can take any vector quantity like gravitational field, any distributed vector quantity like gravitational field, electric field, magnetic field, etc. But to make it simple to understand, we will take very familiar and simple vector quantity, that is velocity. We are all aware with the velocity, and to define the flux we will take flow of fluid, because we all can easily visualize about the flow of flowing fluid. That's why I will take this example of flow of flowing fluid. So flowing fluid, the quantity of flowing fluid, that is flow in liter per second or meter cube per second, whatever unit you can take. So the flow of fluid is nothing but a flux of fluid flowing through a area. So flow is a classic example of flux, and we will understand flux with the help of flow of fluid. Distributed vector quantity for a flux is required. In case of flow, it is velocity of fluid. Second is area. So flow equal to flux. Flux of flowing fluid through an area is equal to velocity of fluid into area. That formula we are all aware with, and this formula is valid when the area is perpendicular to the velocity of fluid. So when the area is perpendicular, in that case flow is given by velocity into area. That is the flux. So we will take simple example to understand and define the flux. First of all, let us take example of a simple rectangular area which is perpendicular to flowing fluid. In that case, so let us take and draw a rectangular this is rectangle, and let the velocity of fluid velocity is perpendicular to this rectangle. Let this rectangle just is A, B, C, D. So this rectangle is perpendicular to this area, and this is N. This N is a perpendicular on this area. N is perpendicular on this area. So in this case, first case, you can easily see. In that case, flow, let the length of this rectangle is L and width is B. In this case, velocity is perpendicular to this surface and the N is parallel to this velocity, and any fluid is flowing through this area. In this case, flow or flux is equal to V into A. Let velocity is in meter per second and area and L and B are in meters. So area is L into B. Area of this rectangle is L into B. So we can say flux of this flowing fluid is V L B meter cube per second. This much of flow is passing through this area, or simple V into A meter cube per second. So this was the case when this rectangle is perpendicular to this velocity. Surface of this rectangular is perpendicular to this velocity. So in this case, just note down, flux is equal to V into A. Now we will take second case. This was very simple case. Both were perpendicular to each other, and whole vector quantity, that is velocity, was passing through. Because velocity has direction, that's why we call this is passing through this area. Any vector quantity can be interpreted as passing through certain area because it has direction and there is an area. So if direction is perpendicular, then it will certainly pass through that area, we can say. Or if direction is parallel to this area, direction of velocity is parallel to this area, then we can say the flow passing through this area is zero. Or crossing this area, the fluid crossing this area when velocity is parallel to this surface is zero. Second case, we will assume, let this area is tilted. Let this area is, this is the axis of this rectangle. So let I am just rotating this rectangle like this, in this direction, clockwise direction. So this was vertical direction, vertical. Angle between vertical and this side was zero in this case. When I have rotated it, then this arm AB, A, and this will be B. This will make an angle theta from vertical. This will make an angle theta from vertical, and this length AD and BC will still remain perpendicular to velocity. Only this length, vertical length AB, will make angle theta, whereas length AD and BC will still remain perpendicular to this velocity. So in this case, let right be there. So in this case, it has been tilted by angle theta. So this normal, which was parallel to vector v, velocity v is still same. So the vector which is perpendicular to this surface will also rotate by angle theta. This n vector which is perpendicular will also rotate by angle. So this was along the direction of v. This was previous position of n. Now new position of n will be let this. So if this has tilted theta, then the n will also rotate by angle theta. And in this case, the extent of flow passing through this area has changed. So we will calculate. Earlier flow was V into A. Now how much flow is passing through this tilted area? So that is the direction of V. Direction of V is unchanged with previous direction. So now we can divide V in two components. That is perpendicular to this area in the direction of n, and along this area, and this component is v sin theta, and this component is v cos theta. This you can easily visualize. Velocity is making angle theta. Velocity is making angle theta with perpendicular on this plane, because this plane has been tilted by angle theta. So this theta and this theta will be same. So component of velocity perpendicular to this area is v cos theta, and along the area is v sin theta. Whereas in this case, v sin theta was 0, because theta, in this case theta is 0. But when it is tilted, it has generated an angle theta, and because of this angle, vector components of velocity in the direction of perpendicular to this area and in the direction of area, two components have generated. So as I have earlier said, the component of velocity which is along this area will contribute zero flow, and the component which is perpendicular to this area will contribute flow, full flow. So flow, because of v sin theta, flow due to v sin theta is equal to 0, because v sin theta is along the plane. So that is along the plane, it will not contribute any flow of fluid passing through this area. And flow due to component v cos theta will be v cos theta into area. So when this area is tilted by angle theta, the total flow will be is both addition of both these components, that is 0 plus v cos theta into a. We can write it v a cos theta. So when this area is making, when the perpendicular on this area is making angle theta with velocity vector, in that case flux is VA cos theta. That is flow, new flow, VA cos theta. Earlier it was VA, now it is VA cos theta. So one method to find the flux or flow when the area is tilted or area is not exactly perpendicular with physical vector quantity is VA cos theta, where theta is angle between velocity and perpendicular on area. Second method, this is one method to find the flux with tilted area. Second method is shaded area concept. Flux can also be found by shaded area method. So how we define shaded area? Shaded area is nothing but, as its name indicates, it is the area of shade. It is area of shade. So in this case, suppose a light source is illuminated along the vector V in the direction of vector P, and this area is placed between light source and this is a film. This is a film where image or shade can form. So in this case, a light source is there. So this, because of this light source, this area will generate its shade on this film. So we will write this expression here. In this case, flux is VA and new flux is VA cos theta. So in this case, when V and area both are perpendicular to each other, the image, when you will see from this point, that this is your eyes, just with your eye, you are seeing shade from there here. So this shade will form on this film. So let this point A is here, this point B is here. So this is the shade of this area. Shade of this area is A, B, C. You will see image shade of this area like this, where the AD is L, both length and width will remain same. AB is L, sorry, and AD is B. So in this case, when this is exactly perpendicular to this velocity, a light source is kept here, and this light source will generate shade of this area. This is the shade. So you can easily see the dimensions of shade will be equal to dimension of original rectangle. AB is L and AD is B. So area of shade will also equal to area of original rectangle. So this area is L into B. That is the original area, A. But in this case, you can see when a light source is kept here, this area, tilted area, will generate a shade on this film. So shade of this area will have different dimension with this original rectangle. So its width is B and this length is L. AB is L and AD is B. That is the same rectangle we have tilted. Now the shade of this area, you will see shade So let the point A B is A dash B, called A dash B on this shape. Similarly, point C and D called C dash D dash. So you can easily see this AD length is perpendicular in both cases to this direction of velocity or direction of source of light. So the length AD will be same, L. This is shape. So you can say A dash D dash is equal to AD is equal to L. Now the length AB is tilted. So it is tilted. The shade length of shade will be less than actual length. So what will be the length? You can easily calculate. You can easily calculate from this triangle. Let this is point P. This is perpendicular. So this length CD and AB both are same because it is a rectangle. So this length is L. CD length is L. And this angle is theta. Similarly, if you draw perpendicular direction, that is vertical direction, this angle is theta, this and this both are parallel. So with vertical, this is making angle theta with vertical. Similarly, this CD will also make angle theta with vertical. This is vertical direction. Sorry, should not confuse with velocity. This direction is vertical direction. So this angle is theta, so this angle will also be theta. This angle is theta, this whole angle is 90, so this is 90 minus theta. And this angle is theta. So you can, from this triangle CDP, you can see CP is actual length of this shade of this dimension CD. So shade of dimension CD is equal to CD is CP, and CP is equal to CD cos theta. CD is AB and AB is L, which can be written as L cos theta. So you can see the shade of this dimension AB or CD is C dash D dash A dash B dash. This A dash B dash is shade of this dimension, tilted dimension. Tilted dimension shade is A dash B dash or A dash C dash. Sorry, C dash D dash. So C dash D dash, that is the shade length, height of this shade is equal to CP. So we can say C dash D dash is equal to A dash B dash is equal to CP is equal to L cos theta. So the length of shade of dimension AB is L cos theta. Sorry, this AD is B, so A dash D dash will be B dash. B. So you can easily understand this whole argument. This length of shade is CP, which is L cos theta. CD dash, sorry, C dash D dash, C dash D dash is equal to CP is equal to A dash B dash, and which is the length of shade of A CD or AB, that is L cos theta. So now the new dimensions of this rectangle, shade of rectangle are B and L cos theta. So the area of this shade is, that is called A dash, will be L B cos theta. You can also write as LB is original area, A is LB, A cos theta. A dash, that is A dash is area of shade. This is shade. Area of shade is A cos theta. So we can say vector quantity into shaded area. Shaded area is equal to V A cos theta, because shaded area is A cos theta. So we can say flux, and this VA cos theta, which we have derived earlier, new flux as VA cos theta. So we can say new flux is equal to VA cos theta, whereas V cos theta, this we have derived by finding components of velocity along perpendicular and along area. Similarly, shaded area, if we multiply shaded area with V, then also we get VA cos theta. So new flux is VA cos theta is equal to V into shaded area. So we can say flux of a vector quantity, physical vector quantity, can be derived by, for a tilted area, by dividing components of vector field along the area and perpendicular to area, and then finding flux due to perpendicular component, because along the area component will have zero flux. Or it can be found by shaded area method, whereas shaded area is always A cos theta. Shaded area is A cos theta, where A is the area of actual shape and theta is angle between normal to this shape and physical vector quantity. So this is one method. Now third method, if we assume area as a vector, if we assume a vector which is called area vector, and this a vector has magnitude equal to area of this shape, and the direction of this vector is along perpendicular to the surface of area. Let n, where n is the unit vector perpendicular to this area. So if we define a area vector as we have defined a displacement vector in line integration, similarly if we define area vector as a vector whose magnitude is equal to area of the given surface and direction is equal to perpendicular on this surface, in that case area vector can be defined. So why we need this area vector? Why we need this area vector? So this area vector is the third method to find the flux. So you can easily see, if we carry out dot product of velocity of fluid into area, vector area, and this is mod of V mod of A cos theta. As we have earlier derived, VA cos theta is flux for a tilted area. VA cos theta has also been derived by shaded area method, where A cos theta is shaded area. Similarly, V dot A will also give us VA cos theta. Always, because A is the vector which is perpendicular to surface. So dot product for this vector V and A, which is simple definition of dot product, mod of A, mod of B and cos theta, where theta is angle between vector A and vector B. And direction of vector A along normal to this surface. So normal angle between normal to this surface and V is theta. So we can find flux by three methods which we have discussed here. And this area vector method is standard method. This is standard method. So we will just prove little bit about circular area. So you should not think that here we have taken example of rectangular area. So the shaded area method or vector area method is true for all types of area, whether it is rectangular or it is circular or it is triangular, whatever it is. So we will just take example of circular also. Let this is a circle and the shade of this circle is when the surface is perpendicular. This is normal to this surface of circle and radius of this circle is r. So we will find shaded area of this circle when this is perpendicular. So in that case there is a source of light. In that case, in this film you will get image of circle. Full circle. Sorry, this is not exactly circle, but actually you will get full circle image. And the radius is r. In this case, when the end which is perpendicular to the circular surface is along the direction of vector field V or source, in that case the image of circle and actual circle both are same. And this area is pi r square, actual circular area, and image, this is shade. In area of shade is also pi r square. Now you just tilt this circle, that we have tilting this circle from vertical now this n, this circle has been tilted along this axis, so this is making angle theta from vertical. Similarly the n, and this is direction of V, that is direction of V. Here V and n both were parallel. In this case this is direction of V, and the n will also rotate by angle theta. So it will make angle theta with vector quantity V. That here you have placed the source of light. In that case, please let this is point A, this is point B, and this is point C, and this is point D. So the length AB will have its shade. The length of shade corresponding to AB will decrease, and this CD will remain same, just like rectangle example. The B was same, whereas L was changed. Similarly here, this is R, R of radius of circle. So this is O. Let the center of circle is O. So this is O. Shade of this A point is A dash. So in this case, new value of its radius, this is R, this angle is theta, so this angle is also theta. Let this A and this is point P. So AP is r cos theta. So when you will see this shade of this circular shape on this film, you will get the shape of ellipse. You will get an ellipse. So this point A will come here, A dash, and this point B will come here, sorry, B dash. So, and this is center. So this CD, C and D, this is point C and this is point D. So length of CD is 2r, so this will remain same. We can say O. So this length of this ellipse will remain same because CD is still perpendicular to the direction of source of light or direction of velocity. Hence CD will have length 2r or OC will have length r. But length AB, the shade of this dimension, will be equal to OA cos theta, that is r cos theta. The shade of OA, only shade of OA is r cos theta. Similarly, shade of OB is also r cos theta. So we can say this minor axis is r cos theta. When this area was tilted by angle theta, the shade of this circular area will be a elliptical area. The circular shape will convert into elliptical shape. And the major and minor axis of this ellipse are r and r cos theta. This is shade. Area of ellipse is given by pi a b. So area will be pi r into r cos theta, and this is pi r square cos theta. OC is A and OA dash is B. Then area of ellipse is given by formula pi a b. That is standard formula for area of ellipse. Just like area of circle is pi r square, area of ellipse is pi a b. So just put a is equal to r and b is equal to r cos theta. So you will get pi r square. So this new area of ellipse is nothing but you can write it a cos theta, where a is area of circle, original area of circle. So in this case also you have seen, in circular case the shaded area is a cos theta, and which was true for rectangular case also. You can say the shaded area is always a cos theta, where a is original area of surface and theta is angle between normal to surface and direction of vector field V. That is direction of vector field and that is direction of normal to the surface, and theta is angle between both these vectors. Or we can say theta is angle between vector A and vector V. Vector A is, here vector A is pi r square, and pi r square is area, that is modulus of this vector, and n is a unit vector perpendicular to the circular surface. So n will always have direction along this n which is perpendicular to this surface. So we can also say theta is angle between vector V and vector area, or vector V and perpendicular to the surface of it. So we will summarize this observation and take a small example to illustrate all this discussion. So we will summarize the whole discussion. Flux is defined as extent of physical quantity, vector physical quantity passing through a surface. That is just simple definition of flux. There is a physical vector quantity like velocity. We have assumed here for simplicity, velocity of fluid. This is vector quantity, and flux is flux, or you can say flow of fluid is equal to, for a area, I have already told you the shape of this area doesn't matter. It can be rectangular area, it can be circular area, it can be elliptical, it can be triangular, it can have any shape, that doesn't matter. We have proved shaded area for circular, for rectangular. In both cases, shaded area is A cos theta. So hence, the shape of area, it is rectangular, circular or triangular, doesn't matter. So this is area, and the normal to this area is this. Hence, velocity v and normal to area is making angle theta. Flow can be given as flow flux, or flux can be given as, first, by dividing velocity in perpendicular and along the surface of area, that is v perpendicular into area, and this will be v cos theta into a, that is v a cos theta. Only perpendicular component which is along the end, this is v, component of velocity along v is called v perpendicular, and component of velocity along the area is v parallel to area. So flux because of this component are zero. Flow because of component of velocity, and this component is v sin theta. V sin theta. So this v sin theta component of velocity which is along the area doesn't contribute for any flow of fluid passing through this area, and this component is zero. Other component v perpendicular, which is perpendicular to this area along the end, this component is v cos theta. V perpendicular is v cos theta. So this v cos theta component is perpendicular to this area. Hence, this completely contributes to flow or flux of fluid. Hence, v cos theta flowed because of v cos theta, which is perpendicular to this area A, is v cos theta into A. V cos theta into A, and v cos theta is perpendicular component. This is actually perpendicular component, v perpendicular, this component. And we get flow is equal to v cos theta, va cos theta. Second method is shaded area method. Shaded area method. Shaded area method is flux is equal to velocity into shaded area. This shaded area is same for any shape. Again I will repeat it. Shaded area doesn't depend on shape, rectangular, circular, triangular, hexagonal or any polygon, whatever it is. Shaded area is always equal to v into a cos theta. This is shaded area, where theta is angle between v and perpendicular to this area. If theta is angle between velocity and perpendicular to this area, then shaded area of this area in the direction of v is a cos theta. Again I will repeat, if area is A and theta is angle between velocity and perpendicular to this area, then shaded area of this shape along the direction of velocity v is A cos theta. It is irrespective of shape of A. It can be circular, triangular, whatever. So in this case also it is VA cos theta. You get flow. And third method is flow is equal to flux, flow of fluid having velocity v, which is nothing but flux of vector field v distributed in this area A is equal to v velocity vector dot area vector, where area vector is defined as a vector having magnitude equal to area of this surface and direction along the perpendicular to this area. So this, by the definition of dot product, this is also V A cos theta. So flux, you can now easily interpret flux of any field, vector field, is field dot area vector. So in standard form, for a vector field F, through area A, we call flux is equal to F dot A. That is standard definition of flux in mathematical term, in vector form. Flux is equal to field. This is distributed field. It can be gravitational field, it can be magnetic field, it can be flow, velocity, distributed velocity, whatever it is. Dot A is the flux of this field F through area vector, through area given surface, where area is vector A is a vector having magnitude equal to area and direction is perpendicular to this area. We will just take a small example of this flux. So this is the area A and this perpendicular is in this direction. Area is equal to 2 meter square. It has any shape. And this is electric field. E. E is, let it is 5 Newton per Coulomb. E electric field is nothing but force, electrostatic force on unit charge. This is 5. So this is the direction of electric field, that is 5. This angle is 30 degree. So here field is equal to vector E and area vector A is equal to 2 meter per second, 2 meter square in perpendicular direction. So AE dot A, flux, electric flux, we will say electric flux will be calculated by vector E dot vector A. That is E A cos theta. E is 5, A is 2 cos 30 degree. This is 10 cos 30 is root 3 by 2 is equal to 5 root. So this is the flux. That is simple to find by this formula. this was how we define flux for a vector field, distributed vector field through a given area. That is the definition of flux. So it can be calculated by simple formula F dot A, and this formula is only applicable when F and A both are constant. But we know we use integration when this field is varying field. This field is not constant throughout the area, or the shape of area is not flat, it is changing. So we will also discuss how we define area vector for a closed surface. That is, it is a spherical surface. So for a closed surface, it is a convention. It is a convention. If it's a closed sphere, that it is a closed sphere, spherical surface. Here, if you take a small area dA, so it is convention that vector dA, area vector corresponding to this small area, will have magnitude equal to area of this small element, and its direction will be perpendicular to this area and coming outward from the surface. When you are seeing this surface from outside, you cannot go inside the sphere. Just see the surface from outside, and the vector, the normal to this area coming towards you will be the direction of this area vector. So where n is perpendicular to this dA, small area, and the direction is towards the viewer, and perpendicular to this small dA area. That is a convention when you define area vector for a curved surface. For a flat surface, this is a simple circular surface, flat, then area vector is perpendicular to this surface. But for a curved surface, area vector is outward from the curved surface and perpendicular to the surface of it. It can be inward, it can be outward, but as a convention, we assume area vector outward, perpendicular to this area. That is the convention you must remember. So this was definition of flux, how we define flux, how it can be calculated from shaded area, and what is the standard definition of flux in terms of field and area vectors. So we are discussing about surface integration. So surface integration is nothing but the calculation of flux, which we have discussed earlier, for some special cases. So we know, for example, flux phi is equal to field dot A. We know this, we have discussed it. Field dot A is equal to mod of F mod of A cos B. This is a simple formula to calculate the flux. But this formula is only valid when field is uniform throughout the area. Then only we can put value of magnitude of field in this formula. If it is uniform throughout the area, and also area A flat, it is not curved. If area A is flat, only then this theta will be constant. For a particular, this is the area and this is the field F. So This is the normal to the area and this is the theta. So this theta will be constant only when this area is flat. If this area is flat, throughout the area, the theta between normal to the surface and field will remain constant. And similarly, F is also constant throughout the area. Then we can use this simple formula for a particular area where field is constant throughout the area and theta will be constant because the surface is flat. So this formula can be used to find the flux. Flux is nothing but, we have discussed earlier, it is the magnitude, quantity of a field passing through a particular area in a particular orientation. That is the flux. But if, let's suppose, field is changing, at this point field is F1, at this point field is F2, at this point field is F3, at this point field is F4, then you cannot use this formula. Here F are different at different points throughout the area. So this F field value, magnitude of field, you cannot put single magnitude of field throughout the area to calculate flux throughout the area. You have to divide the area. In this region F1 is the field, in this region F2 is the field, in this region F3 is the field, in this region F4 is the field. You have to calculate separately flux for every area, that is F1 A1. A1 is the area of this A1, this area is A2, this is A3, this is A4. F1 A1 cos theta plus F2 A2 cos theta plus F3 A3 and so on. Add all those flux to find the total flux. So when this field is variable, then this formula cannot be used directly. Similarly, if this area is not surface flat, this is curved area. This is curved surface. So what will happen? Like this is a field. So at every surface, this is the normal. That is the normal actually. Let this area is dA. So this dA area will have normal, and this normal and field will make some θ1 angle. And here, this is another dA2 area. This area was dA1, this area is dA2, and the normal is in this direction. So this angle between normal and this flux is θ2. Similarly, different areas will have different normals above the area. Hence, this angle theta will change throughout the area. So this formula cannot be used for a curved surface also, because curved surface, the normal vector to area will have different directions at different points. Hence, the angle theta between normal and field will change, and then Fa cos theta, a single formula cannot be used. You have to find dA flux for this area, flux for this area, flux for this area, and then add all those areas. So that is why the concept of surface integration comes in picture. Surface integration is nothing but a simple integration which we are using in our other physics concept like variable density, variable volume. There also we are using integration because dimensions are not uniform, or whatever physical quantity is not uniform throughout the region. In that case we are using integration. Similarly here, to find the flux, if field is not uniform or if surface is not flat, in that case you have to use integration. So in standard vector calculus, you will find surface flux is equal to, you will find the standard definition of flux as double in terms of double integration F dot dA. in vector calculus, the flux you will find written like this. This somewhere you will find A or somewhere you will find R. R for region. dA is also a vector. So the standard definition of flux in vector calculus you will see like this. This means integration of field into area, field dot area throughout the region. Then this is the region. This is the area dA. So dA will be a vector having magnitude equal to dA area and direction equal to normal to this vector. So this dA f dot dA, you have to find f dot dA throughout the region. By the virtue of the property of integration, we know integration just adds, it is the summation. So for finding throughout the area this small integration, small dot products, we can use double integration. In this region R, this is the region R. So in the double integration, you have two quantities. First is field and second is region R. You will have equation of field and you will have equation of region. Two equations will be given to find the flux through double integration. F, the equation of field which we have discussed for gravitational field, it can be any field. Equation of field will be given and equation of region through which you have to carry out the dot product to find the flux will also be given. This is analogous to line integration where we have discussed two things are given. First is field and second is equation of curve or path. In line integration also, equation of field is given and equation of curve or path along which you have to find line integration is also given to carry out line integration. Similarly, in flux, by double integration, surface integration, it is also called surface integration, you will get an equation of field and equation of region like equation of curve. But another important point is, you should never think that surface integration can also only be found by double integration. This is the standard representation of flux by double integration. But surface integration can also be found by single integration. Just single integration you can find surface integration, only single integration. You should never think that when you will see in vector calculus surface flux written in this form, then you should never misunderstand that this flux can also only be found by double integration or surface integration. It is the property of double integration. That is incorrect. That conception is incorrect. Flux is just dot product of field and area, and it can be found by surface by double integration as well as single integration. Both type of integration you can find flux, but in standard form it is written in terms of double integration. So we will take an example and find the flux with the help of single integration and double integration. Both are flux, both are surface integral. One is found by single integration and second is found by double integration. Similarly, you will find divergence in terms of triple integration. I will next discussion I will explain you how divergence is not related with triple integration. It can be found with single integration also. So line integration, flux, divergence, everything can be found by only single integration. It is nothing to do with type of integration, double or triple. But in standard form, they are written in terms of double integration, flux, and divergence by triple integration. That is standard form. But it can be found all type of vector operations. That is path integral, surface integral, and volume integral, they all can be found by single integration. So we will take an example. So we will discuss an example where we will find surface integration or flux by single integration and by double integration. Both methods will be used to find the flux. To avoid the confusion, as we see in standard form, flux is written in terms of double integration. So it is not the exclusive property of double integration. Any type of mathematical operation you can carry out to find the flux. It can be single integration also. Similarly, for divergence type problem where triple integration is written as in standard form in vector calculus, then divergence in a volume can also be found by single integration. So this is the problem. Here, this is the reason. For simplicity, for explaining purpose, we have assumed a circular region given by the equation x square plus y square less than or equal to 1. So we all know this is the circle of radius r, and as it is less than or equal to 1, so this is the region. We will write it separately. So the region which we were discussing is given by x square plus y square is less than or equal to 1. So two equations are given. First is equation of flux and field, and second is equation of region. So here field is velocity. Field is velocity, and velocity, this a fluid, let us assume a fluid is flowing through this circular cross section. It has different velocities at different point in this region because it is a function of x, and this is k. This is unit vector in vertical direction. This is x-axis, this is y-axis, and z-axis is vertical dimension. So v is given by x k throughout this region. So v is variable. Here v is variable. Velocity is variable. It is changing. For simplicity, we have taken very simple function to explain the concept. It can be a complicated function also, as we have discussed earlier. The function of g, vector field g, was complicated. Here we have assumed simple function xk, that is the velocity in this region, and the equation of this region is x square plus y square is less than or equal to 1. So x square plus y square is equal to 1 is a circle, and less than or equal to 1 means the whole region of this circle will be covered with this equation. So we have to find flux of this field through this region. Flux of this field through this region, that we have to find. First method we will use single integration, and second method we will use double integration, because we have earlier discussed that flux or surface integration is not a property, exclusive property of double integration. It can be found by single integration also. But standard form, it is written in terms of double integration. So we know, so here flux is nothing but flow, Q of fluid will be flux, Q. So we know the velocity is changing at every point, so we cannot directly find flux by V into area. Velocity into area, that is the formula for flow, but this cannot be used because velocity is changing at every point. That's why we have to use integration. So we will consider a small strip. A small strip of area. This is the center, and this is at a distance x. Another important thing is mentioned here. Velocity is given by xk. That means in positive direction x is positive. So this velocity will be positive k, some constant into positive k throughout this region. In right half circle, in this right half circle, throughout the region, velocity is upward. That is, x is positive, hence velocity will be upward direction. That is plus k direction, positive direction of z axis. But in this direction, so that this is right half and this is left half. In this left half, x is negative. Left half, x is negative. So this velocity is downward. X is negative, so it will be minus k, minus some constant into k based on the location of y. So it will be downward. So throughout this left half, velocity is down to the board, and throughout the right half, velocity will be above the board. We know this point is minus 1, 0 and this point is 1, 0. This is a circle of radius 1. So we can say the flux for right half, which is flux is field dot area vector. So again, this area vector will have direction constant in right and left half. In both half, to define the direction of area vector, we have already discussed. For a flat surface, area vector is mod of A into vector n, that is unit vector n, normal to this area. Now you can assume two normals. One is upside above from the board and second normal downward to the board. So area vector can have two directions for flat surface. But whatever direction you are choosing, above the board positive and below the board negative, one option is this, and second is this, below the board positive and above the board negative. Once you choose any direction, positive or negative, that is freedom up to you. That is your freedom to choose any direction, any normal direction as positive, and opposite direction you have to choose negative. That doesn't matter. For this area, suppose for this area, I choose above direction, above the board direction positive. Then I have to choose below the board direction negative. Or if I choose below the board direction positive, then I have to choose above the board direction negative. That doesn't matter. You can choose any direction, positive or negative, but once you have selected particular direction positive, then you have to stick throughout the solution of problem, you have to stick to the assumption of direction which you have chosen. Whatever direction you can choose, that is up to your freedom. But for convention, it is convention that above the board direction is chosen positive and below the board direction is chosen negative. You can choose below the board direction positive also. It is up to you. And you will get same result. That result will not change. But convention is that above the board is positive and below the board is negative. For a flat area, there will be two normals. We know any normal direction you can choose positive and second negative. That doesn't make any difference. But for curved area you don't have this choice. You doesn't have this choice for curved area. For curved area, you have to choose. Suppose this is curved area, this is dA. So this direction and when you see this surface from outside, from convex side, when you see, you have to choose the normal direction of this small element area dA as the direction of its vector, area vector. Here you cannot choose this direction of dA. Here it is fixed. For curved area, please remember, for curved area, when you see from convex side, the area vector will have direction outward from this convex surface towards the viewer. The area vector will be towards the viewer. You cannot choose it along the viewer or towards the concave area, concave region. You have to choose it in convex region. So in our case, this is the area, small strip we have chosen, and we have assumed that the velocity is constant. Let this is dx, the width of strip is dx, and we have assumed that throughout this dx the velocity is constant. This is very small. That is the way we use integration in physical problem. We assume a variable quantity and assume that that variable quantity is constant throughout the region, small region. This is a small distance dx. From O at distance x, a small strip of thickness dx is assumed, and it is assumed that velocity is constant throughout across this strip. Across this strip, velocity is constant. So first of all, we will find flux through this strip. So flux df, and this will be dq. Flux here it is flow. So dq will be velocity vector dot dA, area vector. Area is area of this strip. So velocity. So here dA is width is. To find the dA, you can use simple geometry. This is x and the radius is 1. So this is 1 minus x square, under root 1 minus x square. This half strip. Similarly, full strip is 2 into under root 1 minus x square. So dA, area of this strip is 2 under root 1 minus x square dx. This is the area, sorry, this is the magnitude of area. Now area vector, let we have assumed the direction, normal direction above from the board is positive, and the vector in that direction is k, plus k, in positive z direction. So dA will be 2 under root 1 minus x square dx k. That is area vector. So area vector corresponding to this small strip, thin strip having thickness dx and length 2 under root 1 minus x square. So this is radius 1. So this will be under root 1 minus x square by Pythagoras theorem. So this is 2 into under root 1 minus x square. So that is the area vector. Now dq, flux df or dq, flux through this small area will be flow through this small area is nothing but v dot dA. Flux is f dot dA. We have assumed velocity constant throughout this thin strip. So this is x k dot 2 under root 1 minus x square dx k. K dot k is 1. So dq is 2x under root 1 minus x square dx. So we have found dq is equal to 2x under root 1 minus x square dx. Now we know flux for this half is positive and flux for this half is negative. So if you will calculate flux for minus 1 to 1 limit, then you will get 0. That's why we are calculating for half, only one half, so that we can get some value. So we will calculating flux only for right half. Let this is called Q R, means right. This is flow for half circle, and this will be 0 to 1. limit will be 0 to 1. You can take 2 out. X under root 1 minus x square dx. And this can be written as 2 minus 1 by 3. So this can be written as 2 minus 1 by 3 and 1 minus x square power 3 by 2, 0 to 1. That is the integration of this. You can find out. We have calculated here. Integration of x under root 1 minus x square is this. So this can be written as 2 minus 1 by 3. You can take out. So it is minus 2 by 3. This is 1 minus x square power 3 by 2. 0 to 1. And this is equal to minus 2 by 3. For 1 is 0. And for 0 it is 1. This is plus 2 by 3. So if the dimension is in meter and second, this velocity is in meter per second and the radius is 1 meter, then this will be meter cube per second. That is flow, QR. Flow through right half, or we can say flux of vector field V. Vector field V for the right half will be 2 by 3, plus 2 by 3. And here also you can assume plus, why this plus sign is appearing here, because both vectors, that is vector V and area vector, are in same direction. Vector V in this region, x is positive, hence throughout this region vector V is positive, that is above the board, plus k, that is above the board. Similarly, dA is, we have assumed dA is magnitude of this strip, and the normal direction above the board we have assumed positive. Below the board we can also assume positive, that is up to you. You will get same result, but above the board we have assumed positive. So both are in same direction. Vector V and vector A in this region are in same direction. Hence V dot A is positive. Our flow is in above direction. If you assume below direction is positive, then this will be negative. V will be same in above direction and area will be in below direction. Both vectors are opposite, so dot product will be negative. That means the flux along the field is negative. Along the field means along the velocity. Velocity is in above direction and area is in reverse direction. So we can say flux along the velocity is negative if the below direction we are assuming positive. And for right direction you will get flux opposite. In this case you will get flux positive in this half and negative in this half. But if you assume the below direction positive, then flux will be positive in this half and negative in this half. Physically there doesn't make any difference. So here it is plus. Now we will calculate flux left half. We will calculate flux for left half. For left half, we will assume a strip here. So we will get dq is equal to v dot dA. Here you need not to put v is equal to minus xk, because you may think that in this direction x is negative. Then integration will take care for that. Not to bother about that. But for your understanding why it is coming positive and other case it is coming negative, that's why I have mentioned that in this half both vectors are positive, velocity and area vector, and in this half velocity vector is downward and area vector will be same, because that is our convention for area vector. We have assumed for normal area vector in above term of board as a positive direction. So here also area vector will be positive, like here. In both case area vector will be above the board, but in this half velocity vector is below the board. So dot product in this half will be negative. V dot dA. So V is xk and dA is x under root 1 minus x square dx k. That is 2 into x. So radius of this will be same as under root 1 minus x square. So I have directly written as velocity. This is velocity and this is dA. That is 2 into under root 1 minus x square, that is full length, into dx, that is the area, and sorry, this x will not appear here. 2 into that is the length of strip and width of strip, that is area, and k is the positive direction which we have assumed in our assumption. The normal above the board is positive, that we have assumed. So we have to stick with that assumption throughout the problem. So with this you will get 2x under root 1 minus x square dx. Dx. This is flux or equal to dq. So this is distance x. This is dx. Now to find full flux in this left half, we will say QL. Flux for left half is QL is equal to under root. The limit will change from -1 to 0. 2x under root 1 minus x square dx. So the same expression we have achieved here, x minus 1 by 3 1 minus x square 3 by 2 minus 1 to 0. Integration of this is we have directly put here the value of integration. So this is total flux from left and this will be minus 2 by 3 minus 1 by 3 we are taking out 1 minus x square 3 by 2 minus 1 to 0 to be minus 2 by 3 1 minus x square over 3 by 2 minus 1 to 0. And this is minus 2 by 3 into, put 0 here, this is 1 minus, put 1 here, this is 0. So this is minus 2 by 3. So here we have got minus 2 by 3, and if we assume these units, it will be meter cube per second. So the flow is minus 2 by 3, that is in the above half flow is towards upward above the board, and this half x is negative, so velocity is in reverse direction, flow is downward. So it is here both vectors are in opposite direction, that is area vector is above the board, and velocity vector x is negative down the board. So both vectors are in opposite direction, hence dot product in this region, left region, is negative. So hence total flux through this area is plus 2 half plus 2 by 3 minus 2 by 3 is equal to 0. Net Net flow is QR QL plus QR. That is flux through right half plus flux through left half. Flux through right half is positive plus 2 by 3. Flux through negative left half is minus 2 by 3. Total flux is 0. So flux is here flux is flow. So total flow through this area is 0. Another important thing, please remember, we have not put x is equal to negative for left half in this expression, but the integration operation will take care to find it minus. That is the logic just we are presenting here, why it is minus in the left half. But you need not to put x is equal to negative in this half. That integration operation will take care of it. So this is the method by first integration. We have found flux. We have found flux of this vector field, which is velocity here, through this region, which is a circular area given by x square plus y square less than equal to 1, having radius 1. Right half has positive flux, the left half has negative flux in equal magnitude, as total flux is 0. That is flux by single integration. Now we will find flux by double integration. So here we will find flux, total flux through this region given by equation x square plus y square less than or equal to 1 by double integration. This is the equation of region, circular region. For equation of upper half, y is positive. In this upper half, y is positive. So y will be plus under root 1 minus x square. And this negative half, y is negative. So equation is y is equal to under root minus under root 1 minus x square. We will take here a small area having dimension dx and dy. Along x-axis its dimension is dx, along y-axis its dimension is dy. So for this area, dA is equal to dx dy. First of all, we will find flux for right half. Flux for right half. This is right half, this is left. So we know flux is equal to dq is equal to v dot dA. So vector dA, you can write vector dA is equal to k, because above the board direction we are assuming positive. Positive direction unit vector is k, so we have used k here. So vector dot dA vector, this dA area, this dA area vector is dx dy. This is the magnitude of area, dx into dy, and k is the direction of k. Flux is v dot dA, and this is xk dot dx dy k. This is k dot k is 1 x dx dy. This is dq flux. That is, we have assumed that the velocity or vector field through this small element area is constant. Velocity is changing with every point. As per this equation, at every point velocity is changing. But this small area is so small, we have assumed that velocity is constant throughout this dA area. So dq will be, flux through this area will be x dx dy. Total flux through the right half will be double integration. We have to sweep this half, this right half, by this area, that is through horizontal and through vertical movement. This small area will sweep all this right hand region. Then we will find limits. So this will, in x direction, maximum limit is 0 to 1. and in y direction this equation of this curve is minus under root 1 minus x square, and it will sweep and it will reach here. Equation of this curve is plus under root 1 minus x square. X dx dy. So this is the range of this small element 0 to 1 in x direction and minus under root 1 minus x square to plus under root 1 minus x square in y direction. With this range, this small element will sweep all this right hand half area. Now we have to find flux. This is flux through right hand half area. This can be written as 0 to 1. First of all, we will integrate with respect to dy. So this is x and this can be written as y minus under root 1 minus x square. This is plus under root 1 minus x square and this is dx. And this can be written as 0 to 1. First limit and then this is the second limit. So this is 2x under root 1 minus x square dx. So this can be written as 2 minus 1 by 3 1 minus x square 3 by 2 0 to 1. That is the integration of this. Directly I have written here. That is the same expression in single integration, which you can remember. In single integration we have got same expression. So we will get same result. And this will come as 2 minus 2 by 3 0 minus 1 and this is plus 2 by 3 meter cube per second. That is the value of flow or flux through right half. Through right half it is plus 2 by 3, which we have discussed why it is positive. Because in right half both vectors are in same direction. Vector v and vector dA, area vector, both are in same direction. Hence flux in the right half is positive, because dot product of vectors in same direction is always positive. Now we will find it for left half by double integration. For left half, let a small element area dA. Along x-axis its dimension is dx, along y-axis its dimension is dy. So dA will be dx dy k. We have assumed normal above the board is positive and normal below the board is negative. So here dA will be positive because above the board normal direction we have assumed as the direction of area vector, which is k. K is the unit vector in above the board direction, that is positive z direction. So dq for this half, dq flux is equal to dx dy k dot v dot x k. K dot k is 1, so this is x dx. Again, for total left half flow will be by double integration. This area will sweep the whole half region, left side half region. So x direction limit will be minus 1 to 0, and in y direction equation of this is also plus under root 1 minus x square, and equation of this is minus under root 1 minus x square for this half. And for this half equation is plus. So limit will be from minus 1 under root 1 minus x square plus under root 1 minus x square. X dx dy. Again I will remember you that here you need not to put x is equal to negative in this velocity vector or field vector equation. The operation of integration will take care for that. Will automatically give you flux negative. Let us go ahead.
First of all, we will integrate with respect to y x. This is y dy. This is minus under root 1 minus x square. This is plus under root 1 minus x square. It can be written as minus 1 0 2 x under root 1 minus x square. And this can be written as 2 integration of this is minus 1 by 3 1 minus x square d by 2 minus 1 0. And this can be written as minus 2 by 3 minus 1 by 3 we have taken out. So first of all we will put minus, we will put 0, that is 1 minus, we will put minus 1, that is 0. So this is minus 2 by 3 meter cube per second.
So flux from left half is minus 2 by 3, whereas flux from right half was plus 2 by 3. The same result we were getting by single integration. The same result we are getting by double integration. So flow or flux through this right half was 2 plus 2 by 3 meter cube per second, and flow or flux through left half is minus 2 by 3 meter cube per second. So the total flow or total flux through this area for the vector field this, which is velocity vector of flow, is 0. So here we have seen that we have found flux by single integration and double integration. For a field which is given by velocity of a fluid through this region, this is field xk and this is the region. So here the equation of region is this, which we were using in double integration, r f dot dA. So here we were using in double integration equation of region. We need two quantities, that is equation of region, which is given by this x square plus y square less than 1 or equal to 1, and equation of field, which is v. Here it is field is velocity vector distributed field xk. With these two parameters we can find flux either by single integration or by double integration. But in standard form you will read flux written as this expression in vector calculus. Flux will be written in terms of by this expression of double integration, which you should never confuse with that flux is the only property of double integration. It can be found by single integration also, f dot dA. So I was just trying to explain that flux is not exclusive property of double integration, or surface integration is not an exclusive property of double integration. It has nothing to do with double or triple integration. It is just a flux by its definition. It is the f dot a, field dot area vector. Whatever method you find simple, you can use that method. Even sometime without integration you can find flux for simple problems like constant field and flat surface. When these parameters are changing, that is field is changing or surface is not flat, in that case you have to use integration. For integration also, if you find single integration simple, then you can use single integration to find flux. If you feel double integration simple, easy, then you can use double integration to find flux. It is up to you. You have to decide what type of method you want to select to solve the problem, to find the flux.